All right, we're going to work to solving problems with forces that are at angles, using Newton's laws to solve problems with forces at angles. So we're going to take a look specifically at problems number 4 and 5 on the applications of Newton's laws. Worksheet, taking a look at those. Okay, so for number 4, what's involved in our system? Of course, we have the airplane. And we have the air. You can say that you have your engines in the airplane, but those are basically sending air out. We're going to look at this all together. So basically what you have is the air pushing on the airplane in a thrust force. Then you have air resistance in a drag force that's going to be pushing back on the airplane. Sorry about that. And of course, also in our system, we always have the earth, right? So we have the earth that's going to cause there the force of gravity on the airplane. So if we draw all these forces and we have our airplane flying in through the air, right? We have a thrust force pushing it forward. And we have our drag force resisting it. So that's our force due to air resistance. And of course, we have the weight of the plane acting straight down, force of gravity. So those would be all the forces acting on the plane. Drawing our free body diagram, force of gravity, or the weight acting straight down, our thrust force. Whoops, I think I did forget a force. We also have we'll just continue here. We have the force of air resistance, but you're also told that there is a lift force on the plane perpendicular to the wings. So that lift force would be up like this, perpendicular to the wings. So our lift force is going in that direction, which means, and then the plane is flying at an angle of 30 degrees with respect to this horizontal line. So what we notice here is lift and air resistance and thrust are along the same lines and perpendicular to one another. So if instead I take a look at the direction of motion along this line to be my x, perpendicular to that is my y. So the only force giving us a problem here is the force of gravity. So what we need to do is take a look at this and say, well, instead of using the force of gravity, I want to use its components that are along the y and along the x. So what's important here is that your force that's along the x is parallel to the x direction. Do not write it down like this and then come across in this direction, because that means the x and y are not perpendicular to one another. These two must be perpendicular. That's the definition of your x and y. So here's our perpendicular angle in here. This is also 90 degrees, and so is this angle to be 90 degrees. So if this is 30, then this is 60. And if this all has to be 90 degrees within here, I drew that a little bit too long, then this also must be 30 degrees, which means I can break up these components. This is going to be FGX, and this is going to be FGY. And I can see using my trig, what I really have here, I have FG acting down. Let me write that on this side. I have an FGY and an FGX. So the key is to look at those two components and decide what do they equal in terms of the original vector and the angle. So since this is my right triangle, FG becomes the hypotenuse of that triangle, FGY becomes the adjacent side, and FGX becomes the opposite side. So the cosine of any angle is equal to the adjacent side, which on our picture is FGY, divided by the hypotenuse. So FG times the cosine of the angle theta is equal to FGY. The sine of the angle theta is opposite, which is FGX, divided by the hypotenuse, FG, which means FG sine theta is equal to FGX. So there's two equations that I now have that will tell me what FGY and FGX are. So I'm going to do that immediately, right, when I'm cleaning this up. Now I'm going to come over here and I'm only going to draw my X and Y components. So what I have is an FGY and FGX in my X and Y components. I have a thrust force. I have a lift force. Oops. And I have a drag force, or the air resistance force. So those are all my forces, all at right angles to one another. If that bothers you to look at like that, you can certainly twist your paper and go back and redraw it in the true vertical and horizontal that we are used to. FGY, FGX, air resistance, thrust force. Try that longer because it, of course, has to overcome air resistance and the weight. And finally, lift force. So again, what's involved in our system? What forces would be present? Drawing all those forces according to the rules of how they would act. Gravity always acts straight down. Air resistance is always parallel to the direction of motion, and resists motion. So when I draw all the forces that are present, I want to get rid of any that don't fall along with the X and Y component. Based on trigonometry, I can solve for those two components. Put those components into my free body diagram, all being drawn in the horizontal and vertical direction. Now we want to say, okay, what do I know and what do I want to know in this problem? So we are given that the angle is 30 degrees, right? So if I want to list what I know, and what do I want to know? So we're told that theta is equal to 30 degrees, and that is the angle that I want based on what I chose to be sine and cosine. We're told that the force of gravity is equal to 86,500 newtons. The thrust force is equal to 103,000 newtons. We're also told that velocity is constant. And that's important because that tells us that AX is equal to 0 and AY is equal to 0. And that's why you pick the directions of motion that you do. I always make the direction of my motion, unless it's true vertical motion, to be along the x-axis. So what we're looking for here is, what is the lift force? And what is the air resistance force? So we don't have specific equations that contain those two variables, but what we would do next is make Newton's law fit our diagram, right? So what do our equations tell us? So remember, we always want to do it in the x. And the y. So if I add up the forces in the x, I have a force thrust. Going to add to that the force of the air resistance plus the force of gravity in the x direction equals MAX. In the y direction, you simply have lift force plus force of gravity y is equal to MAY. Writing them with magnitude only, taking anything to the right positive, to the left negative, anything up positive, and down negative. I would have the magnitude of the thrust force minus the magnitude of the air resistance minus the magnitude of the x component to weight equal to MAX. In the y direction, you'd have the magnitude of the lift force minus the magnitude of FGY equals MAY. Okay, so now I have those equations. They fit my pictures, right? In the x, I have force of friction, force of gravity in the x, and thrust. In the y, I just have lift and GY. So where does lift and the force of air resistance show up? So they are in these two equations. What is lift? What is the force of air resistance? So for step 4, I'm going to begin rearranging my equations to solve for those, recognizing what is 0 so I can cross this out of my equation. So with that being 0, I recognize that, okay, the easier equation to begin with is that the lift force is going to be equal to the y component to gravity, which I already found to be GY cosine 30 degrees. My GY was 103,000 newtons times the cosine 30 degrees. So that comes out to be 74,911 newtons. On our picture, that is positive x direction. Sorry, positive y direction. I want to solve for air resistance. Getting this all by itself, I can either take it to the other side, so I'd have the force thrust, so I can get rid of the negative, minus the force of gravity in the x is equal to the force of air resistance. So the thrust force we were given to be 103,000 newtons minus Fg sine theta equals force of air resistance. So do you know these values? I'd get 103,000 newtons minus, wait a second, sorry, wrong number over here. This should be, got the right answer there, but 86,500, right, newtons. Over here, we get 86,500 newtons times the sine 30 degrees equals your force of air resistance. And that comes out to be 59,000 positive, which tells you you assume the right direction for that motion, and the air resistance is equal to the air resistance forces that act on this airplane. So again, being in the positive, that means you chose the right direction from the beginning, and it is going in that direction. So again, to summarize, we've done the same thing in each problem. Right? What's part of our system? What forces are present? What direction do those forces act? Are any forces balanced because there's no acceleration? And then writing what you know, what you want to know, breaking up the force into its components. So the force that is not along your set X and Y direction, you must break up into components. Follow the same process, summation of forces in the X and Y, putting in your values, and solve. Okay, let's take a look at number 5. A mover is placing a 65 kilogram box on a truck, sliding it up the ramp, which makes an angle 40 degrees with the horizontal. The coefficient of sliding friction between the box and ramps is 0.7. So remember, that's the mu value that we looked at in the laboratory. And he pushes with the force of 445. What will be the acceleration of the box? So let's go ahead and solve for this one. I might go ahead and scroll. All right, so in this case, we have an inclined plane and a box being pushed up the inclined plane. So remember, this on the surface means that surface is not moving. So what do we have part of this system? Here we're going to have the box. We have the ramp. We're going to have the surface. Definitely going to have the earth. We have, is it Tom? What's our person's name? A mover. So we'll just say the mover. Okay. And I think that's it. So with these forces, what you know is the surface acts on the ramp. The ramp is what acts on the box with a normal force and friction. So I'm going to label those separately. The earth pulls down on the box, gravity, and the mover is pushing up on the box to keep it from sliding back down so much. So if we were to make our boundary system right here, we should have 4 forces acting on this box. So the first force, of course, always weight, which acts straight down. So that's our force of gravity. You were told that the motion, he's trying to push this box up the ramp, which means our force of friction is to oppose that. So we might have the force of friction here. So it's opposing the motion. Tom is pushing on the mover or on the box, right? So that's the force applied by an outside person. And then we also have this normal force that is also due to sitting on top of something else, right? So that's it. Those are all your forces. Again, drawing them over here, putting all the forces in. I can take a look to see that, okay, I have my force of friction. Whoops. I want that to come the other way, right? Force of friction, normal force, force applied, and weight. The weight always acts straight down, right? So taking a look at all those forces, you can clearly see, just like the airplane problem, where we have, they are not all in the X and Y direction, right? So if we choose this direction of motion to be our X and this direction of motion to be our Y, then it's the force of gravity again that is giving us the issue. So we'll break this up into components, coming along the Y, coming along the X. So that's going to be FGY, and this is going to be FGX. This is FG, FGX. This is the angle theta. That's going to be the same as this angle here. So again, seeing why that is, if this angle here is 90 degrees, when I drop a line in here, right, going across, this also is 90 degrees. So these two angles must be the same because they share the same complementary angle there. So breaking it up into components, again, sine theta is equal to opposite FGX over your hypotenuse FG. So FG sine theta is equal to FGX, and cosine theta is equal to the adjacent side, FGY, all over FG. So FG cosine theta is equal to FGY. Redrawing all of that, to clean it all up, you will have FGY, FGX, friction, normal force, both due to the surface, and finally the force applied by the mover. If you want to rotate that, up to you. It's hard to visualize that. You can turn it all to 30 degrees and have FGY like that, FGX, normal force, friction, and the applied force. So if we continue taking a look at all these forces and listing what we know, we do know that the acceleration in the y is 0. There is no motion bouncing up and down, right? So we can make a note of that. If acceleration in the y is 0, then that means these two forces must be equal to each other. So we can say the force of gravity in the y is equal to the normal force, right? The magnitudes of those. So they are in opposite directions. We cannot say these forces are equal in the x, even if acceleration in the x is 0, because, and that's what we're looking for, the acceleration, because there's more than two forces acting in the opposite. So even if acceleration in the x is 0, we wouldn't assume that those are all equal. All right, so given more information about what we know and what we want to know, right? So in this problem, we were told that the mass of the box is 65 kilograms. So immediately solve for the force of gravity, right? Which is going to be mg in the same direction as acceleration due to gravity. The units of kilograms are good. If it was in grams, we would want to change that. Times 9.81 meters per second squared. So we get the force of gravity, magnitude, equal to 637.65 newtons. The vector of that would be that that's acting straight down, right? We're told the angle of incline is 40 degrees. The coefficient of friction between the surface and the box is 0.47. Remember, that's dimensionless. That is just a number for the surface. And the mover is pushing on the box with a force equal to 445 newtons up the ramp. We already said that there is no acceleration in the y, so that will be 0. And we are looking for the acceleration in the x direction. So again, same process. What's part of your system? What forces exist? What direction are those forces acting? How are they acting? What is the direction of all these forces? Making them all in the x and y direction. Listing what we know, what we want to know. Now next we take a look at equations. So summation of forces in the x equals max. Summation of forces in the y equals may. So looking at these equations and going back to our diagram, right? All of our forces in the x and the forces in the y, we've already established that they are equal to each other, but we can set that up in equation to prove that. So in the x direction, right, we have the force of the mover, or force applied, plus the force of friction, plus Fgx equals max. In the y direction, we have the normal force plus Fgy. So we're solving for ax, right? Here in the y direction, we know that this ay is equal to 0. We're solving for ax. We do know mass. We can solve for Fgx because we know theta. We don't know the force of friction. And we do know the applied force. So to solve for the force of x, we're also going to have to add to our list of unknowns. What is the force of friction? So another equation that I'm going to want to consider is that the force of friction equals mu times your normal force. So I see here in the y that I can say, okay, my magnitude of the normal force is equal to the magnitude of Fgy. I'm going to use that up here. So that means my normal force is equal to Fg cosine theta, which Fg we found to be 637.65 newtons, cosine 40 degrees. So plugging that in, we get our normal force. I get that to be 488.47 newtons. we're going to use that to find the force of friction. So now I can say the force of friction is equal to mu, which is 0.47 times my normal force of 488.47 to give me my value, my magnitude of the force of friction. And multiplying those two together, I get 229.58 newtons for my force of friction. So I will use that value now over here, right? So putting that over to here to solve for my acceleration in the x. So rearranging the equation to get ax by itself, I'm going to have to divide both sides by mass. And I will get the magnitude of the force applied minus the magnitude of the force of friction minus the magnitude of Fgx all over my mass equals my acceleration in the x. So keeping in mind that over here, this gives us the magnitude of the force of friction. It always opposes motion, right? So over here, we have the force applied minus magnitude of the force of friction minus Fg sine theta all over mass. That's going to be our acceleration in the x direction, magnitude. So we get 445 newtons minus 229.58. So we got 229.58 minus 637.65 times the sine of 40 degrees all over 65 kilograms. So these are all newtons, right? Equals AX. So Newton divided by a kilogram gives you a kilogram meter per second squared divided by a kilogram. You end up with meters per second squared, which is what we want for AX. So what we get here is a negative value, 2.99 meters per second squared is your acceleration in the x, which means that motion is actually in the opposite direction. So motion would be going down the incline. We assume the wrong direction of motion. So that's the acceleration we get in this problem. So again, reviewing, right? Seems pretty long. All the more reason we need to be organized as we're taking a look at our problem. So we have what's in our system, what forces are caused, what is not in our x and y direction, breaking it up into components, drawing everything in the x and y direction, solving Newton's equations to fit our picture, considering vectors and their direction. We are always taking to the right to be positive, to the left negative, up positive, down negative. So again, I'm writing these as vectors and I'm adding the vectors. When I add their magnitudes is when I consider positives and negatives.